Okay, so now we want to think about waves and derive the wave equation, and then come back to Maxwell's equations and show that we get a wave equation in charge and current-free regions. So what is a wave? Let's say that on the y-axis we have something that represents the displacement of the wave. So how high is the wave? What is the amplitude of the wave? Say something like that. Right, so that this is sort of a spatial x direction, and this wave at some moment in time is just a displacement in space that looks like that, and then later in time it's going to move. We want this disturbance, or you can imagine that you plucked a string and that disturbance propagates in time along the string. It looks something like that. So what is the mathematical expression? Well, this amplitude is a function of x and t. So we were looking for a function of x and t that captures this kind of behavior. Well, this represents some kind of value of the function over some range in x. And what we want is that, so if this represents t equals 0, this is the form of the function at t equals 0, we want to have that same value at a later time, representing the idea that the disturbance is moving along the x-axis. So at t equals 0, t is 0, we get we have some value of x, but now we want that same value to happen at a later time. So a different value of x and a different value of t. So let's say, maybe we could imagine this being x equals 0. There's nothing special about the axis being there. Let's say this is x equals 0 and t equals 0. And this now is obviously x greater than 0 and t greater than 0. So we're going to subtract something that has dimensions of length, and this gives us 0. So there's some non-zero t and some non-zero x for which we still get 0 here, and so we know that this amplitude must have the exact same form because it looks exactly the same as this. All right, t equals 0, and this being 0 is satisfied here as well. And so this is the way to produce a disturbance that travels in space. At an even greater time, right, and an even greater x, this disturbance will be here. So this represents a traveling disturbance. And so, it's any function of x minus vt will represent a traveling disturbance in the x direction. Now, of course, you can have more complicated waves that travel in other directions. But let's say that we have a function y equals, a cosine of kx minus vt. The fact that this is the function tells us that this is a traveling disturbance. In fact, this represents a cosine function that's moving to the right at speed v. And so we want to derive the wave equation. So let's take derivatives in time, dy by dt, what does that look like? It's k v a sine of kx minus vt. And let's take another time derivative to return the function back to its original form, i.e. cosine. We get a minus k squared v squared, a cosine of kx minus vt. And now notice that if we take derivatives with respect to space, in this case x, we get minus k a sine of kx minus vt. And if we take another space derivative, we get minus k squared a cosine of kx minus vt. And we can now relate these two terms. We could think of relating the first derivative terms, but if we consider the two derivatives in both space and time, then we can notice that d2y by dt squared is not quite equal to two derivatives of y in x. They will be equal to each other if we throw in this v squared term. So this is normally the way we think of the wave equation, but we can think of it in different ways. We can relate it to one-time derivative. That's actually what we do in quantum physics. But that's the wave equation more generally, or in terms of two derivatives in space and time.